Algebraic filters provide a generic framework out of which we can extract the commonalities of different forms of convolutional information processing. To substantiate this claim, we have shown that, indeed, it is possible to express familiar convolutional filters in the language of algebraic filters. Doing so requires the specification of vector spaces, algebras, and homomorphisms, which we do in this section for graph, time, and image processing. In order to specify a concrete ASP model, we need to prescribe three objects: a vector space M where signals X live. The prescription of this vector space implicitly prescribes a space of endomorphisms, which is the set of linear transformations that can be applied to signal X. Separate from the vector space M, we prescribe an algebra A where filters H live. This algebra defines the rules of convolutional processing in an abstract sense. The third element we prescribe is a homomorphism row that maps filters to linear transformations we can apply to signals X. The homomorphism translates the abstract filter H to a concrete filter row of H we can apply to signals. Very importantly, the specification of the homomorphism can be reduced to the specification of sheaf operators. These are the images row of G of the algebra generators G. If we specify the mapping of the generators, the homomorphism gets defined for any other filter. This is because filters H are polynomials on the generators H, which are mapped to polynomials on sheaf operator S with the same coefficients. The prescription of M, A, and rho determines the convolutional processing of signal X as the application of the endomorphism rho of H. This allows the use of algebraic models to solve a variety of signal processing tasks, including graph, Graphon time, and image processing, as we describe next. We begin by reviewing graph convolution, which we have already seen can be expressed as particular forms of algebraic convolutions. More to the point, we begin by tackling a graph signal processing task where our goal is to process a signal X that is supported on a graph. The graph has n nodes supporting each of the n entries of the signal X, and the graph is described by a sheaf operator S. GSP in the graph with sheaf operator S is a particular case of ASP in which the vector space where signal live is Rn. The associated space of endomorphisms is the space of square matrices. The algebra is the algebra of polynomials of a single variable, in which filters are written as symbolic polynomials. The mapping to the space of endomorphisms is accomplished by mapping the generator T of the algebra of polynomials to the sheaf operator S of the graph. This results in filters expressed as polynomials in the sheaf operator S, which is, indeed, the object we have called a graph filter. The result of applying this filter to a signal X is simply the multiplication of the polynomial on S with the signal X. Another task that we can solve with algebraic filters is the processing of signals on graphons. The signals that we are given are supported on the interval 0, 1 and have finite energy. They belong to the space L2 of 0, 1. Which contains the functions that are square integrable in this interval. To process signals on graphons, we particularize algebraic signal processing so that the vector space where signals live is L2 of 0, 1, the space of functions that are square integrable in 0, 1. We still stick to using the algebra of polynomials of a single variable. Filters in the abstract are the same as the filters we use in graph signal processing. What changes is the definition of the homomorphism. In the case of Graphon signal processing, we map the generator of the polynomial algebra to the operator T sub capital W. This is the integral function operator that applies the Graphon W of U V to the Graphon signal X of V. This mapping completely defines the homomorphism and results in filters that are given as polynomials on the operator T sub W, where powers of the operator T sub W represent successive applications of the operator. The application of a Graphon filter to a signal X is the application of this polynomial operator to input signals, which is, indeed, the structure we have called Graphon filter. We can now move on to consider the processing of discrete time signals. These are sequences X defined over the integers. They extend from minus to plus infinity. The sequences are required to have finite energy. They are square summable. We say they live in L2 of Z. Discrete time signal processing is also a particular case of ASP. In this case, we have that the vector space where signals live is L2 of Z, the space of square summable sequences. The algebra is, again, the algebra of polynomials of a single variable, same as in graph and Graphon signal processing. What changes is, again, the homomorphism. We produce a homomorphism in which the polynomial T that generates the polynomial algebra is mapped to the time shift operator S. The time shift operator is a linear operator that, when applied to the sequence X, it shifts the time indexes 1 unit up. The new sequence has the same values, but the value at index n after application of the operator is the one associated with the index n-1 in the sequence to which the operator is applied. This mapping of the generator T yields filter instantiations in the form of polynomials on the time shift operator. When we apply this filter, we produce an expression that is not unlike the ones we have seen before, except that the shift operator S is now a time shift operator, not a graph or a Graphon shift operator. An extra level of simplification is possible if we isolate the end component of the output. This can be written as the sum over k of h sub k times x sub n minus k, which is the familiar expression for the convolution of time signals. Yet another example of a task that we can solve with algebraic signal processing is the processing of images. An image is mathematically represented as a sequence with two integer indexes. The sequence is required to have finite energy, as usual. We say that it belongs to L sub 2 of Z squared. To recover image processing as a particular case of algebraic signal processing, we define M as a vector space of square summable sequences with two indexes, the space L2 of Z squared. In this case, we need to use a different algebra, the algebra of polynomials of two variables, made up of abstract expressions we can write as polynomials with two letters. This is an algebra that has two generators, the polynomial x and the polynomial y. We map the polynomial x to the shift operator s sub x. This is an operator that shifts the first coordinate of the two index sequence. We map the polynomial y to the shift operator s sub y. This is an operator that shifts the second coordinate of the two index sequence. This choice of mappings of the generators x and y yields filters that are expressed as polynomials that signify repeated applications of the shift operators s sub x and s sub y. Applying these polynomial operators to the processing of an image x produces an expression that is equivalent to the usual definition of the two-dimensional convolution that is used in image processing. Algebraic convolutional filters encompass graph, graphon, time, and image convolutional filters as particular cases. There are other particular cases that can be obtained, notably group convolutional filters. The value of having built this abstraction is that it provides a framework for analysis that holds for all kinds of convolutional filters. Our particular interest will be in constructing an abstract framework for algebraic convolutional neural networks. Out of this framework, we expect to find abstract stability properties that hold for all particular cases, namely graph, graphon, time, image, and group convolutional neural networks.